Um, so hi, Sudarshan. So we can start, right? Is your voice working? If it's not working, no worries. You can just type in the chat box if you have any doubts at all. Okay. So okay, no problem, no problem. Well, since I guess no one else has joined at any point of time, if you want to stop me, just ping me in the chat box. I will just see it from time to time and then yeah. Okay, so I will start then. Can you just type if my screen is visible? Are you able to see the slides? Yeah, good. Thank you. Okay. So good evening once again. I'm Nandh Kishore from the Department of Electrical Engineering, IIT Delhi. I'm doing my PhD over here in the field of power electronics. So today we'll be seeing the problem solving session on the last topic that you saw in rectifiers, that's PWM rectifiers, but mostly you don't have much problems in that as such. And we will also be seeing some basic problems with DC-DC converters, specifically non-isolated DC-DC converters. So today I thought I will include some more problems on rectifiers because, as you know, in rectifiers you have a lot of topics and I mean, you can have a variety of questions. So I just thought, okay, we can include some more questions just for the sake of variety. We'll see problems from both of them, and if we have time, we can go for more problems in non-isolated DC-DC converters. Okay. Okay. So just as a recap, in the past week, you learned about PWM rectifiers. So in specific, you learned about one non-isolated, one isolated PWM rectifier, that is the boost PFC. We call it PFC because it's a power factor correction stage. So we have the boost PFC, and I guess you also learned about the flyback topology, right? So you learned about the rectifier, I mean PWM rectifiers and the DC-DC converters based on which you implement rectifier techniques. After that, you forayed into non-isolated DC-DC converters. Specifically, you saw what was the buck boost and buck boost converters. So today's problem solving session will include problems from these topics. Okay, so yeah, we'll just see the problem, and most of the problems are, I mean, all the problems include both theoretical as well as problematic. We will just, it's a mixture of both types, so we can just see all of them. Okay, so the average value of output voltage of non-isolated DC-DC converter is controlled by current limit control. This control is possible with which type of load? Inductive, capacitive, resistive, inductive or capacitive, or what? Okay, so I guess this is a pretty easy question. You should be able to tell the answer. The reason being that before you even go into the problem, you can just note down your passive elements, which are your, I don't know why it's not writing. Okay, which are your L, C, and R, right? So you have your L, C, and R. I don't know why my pen isn't working, but okay, so I guess this is an easy problem. So it should be easy to solve. Okay, so you have your L, C, and R, and you also know that your L doesn't oppose sudden change in current, or it opposes change in dIdt, correct? That's why we call the voltage across the inductor to be L times dIdt. So L opposes change in current, and your capacitor opposes change in voltage, whereas your resistor simply follows your voltage, right? The resistor, the current through the resistor is simply proportional to the voltage across the resistor. So if we see by that account, the average value of output voltage is controlled by what, right? So for that, if you see over here, if you have an inductive load, assume that the inductor dominates over the resistor. So if you have an inductive load, you of course know that you have a minimum value of the current and the maximum value of the current, correct? So based on the value of the inductor, the value of Imin and Imax are going to change, right? So that's why you see that when the switch is on or the inductor is charging, you see that the current just doesn't increase. Um, to some preset value. It kind of ramps up from a minimum value to the maximum value. And when it is freewheeling, it again ramps down from maximum value to the minimum value. Therefore, the answer to this question is A, inductive load, right? So an inductor, if you have an inductor, obviously you can control the current. So that's why we call it the current limit control, right? And it can be implemented only with an inductor. Say if you just have a resistor, you obviously know that the current through the resistor is going to follow your uh, voltage across the resistor, correct? So the voltage across the resistor will be a switched waveform due to which the current through the resistor will also be kind of switched. Okay. Okay. So answer is A, inductive. And then we move on to the next question. Which of the following techniques helps to improve the power factor? Extinction angle control, symmetrical angle control, PWM or pulse width modulation control, or all of the above? So I think you went through each of these techniques in detail in the classes. So the answer is all of the above. In particular, you studied about extinction angle control and symmetrical angle control using SCRs or thyristors, and you of course know that um, you have pulse width modulation control as well, which are the PWM rectifiers. Under that category, I think you saw about the boost power factor correction stage or the boost PFC, we call it, and the flyback converter as well. Okay, anyway, so all of these techniques can help improve the power factor. The next question is the variable frequency system control of chopper is also known as dash. So of course, from the name itself, you can understand that the frequency is not fixed. Frequency is changing. So option A, pulse width modulation scheme, B, frequency modulation, C, hysteresis control, and D, none of the above. Right? So in pulse width modulation, you of course know that you are going to change the duty. Correct? So the frequency is fixed, only the on time of the pulse is going to get changed. So that is your pulse width modulation control. In frequency modulation, as you can understand, your frequency, you're changing the switching frequency of the converter within F minimum to F maximum, right? So the answer to this question is variable frequency is obviously frequency modulation because you are modulating your switching frequency. The other one is hysteresis control, wherein you control the current to be within a certain band between a lower limit to a upper limit. So that comes under kind of current control, and it's not exactly your modulation scheme. So you kind of turn on or turn off the device based on the current limit. So if the device current exceeds a certain limit, then you kind of turn off the device, right? So that's your hysteresis current control scheme. Anyway, the answer to this question is pretty simple. It's frequency modulation control. Okay. A single phase full converter is made to deliver a constant load current. Okay. For zero firing angle, the overlap angle is 15 degrees. Therefore, the nu is going to be 15 degrees. Right? Calculate the overlap angle when the firing angle is 60 degrees. So the nu is 15 degrees for alpha equal to 0. So calculate the overlap angle for alpha equal to 60 degrees. Right? Okay. So again, this is another simple problem, I guess, because they have anyway given the converter that's getting used. That's a single phase full converter, right? So for a single phase full converter, you know that the overall angle, of course, you understand that the question about overlap angle comes into play if there is a source inductance, right? So you kind of need to relate your alpha or your angle with the source inductance, right? So you know this particular relation that cos of alpha plus nu, that's the overall angle, firing angle plus the overlap angle is given by this. That's cos alpha minus 2 omega ls by root 2 vs into I naught. Correct? So you just plug in your values of alpha and nu, and you can just get the value of nu, right? So I had to type in these
Yes,
in
sir.
the text. Sorry.
Yes, sir. Yes, sir.
Yeah, yeah.
Hello. Yes, sir. Understood, sir.
Okay, okay. So actually, I had to type in this because my pen was not working from afternoon, so that's why I needed to type in this. Anyway, so I guess this is understood. So the answer is 2.3. If you have any doubts, you can just um You can just go back to the lecture slides. I guess this was given by sir in one of the lecture slides itself. So I have just plugged in the values directly. Okay. Okay. So this is 2.23 degrees. Okay. In a single phase semi-converter with resistive load and a firing angle alpha, each SCR and freewheeling diode would conduct for dash. So the given converter is a single phase semi-converter, right? So you understand that in a semi-converter, you have a freewheeling diode, a dedicated freewheeling diode, in addition to the full bridge rectifier, right? So the question is each SCR and freewheeling diode would conduct for what period? Correct. So for this question, anyway, again, as I told, I needed to type in it. So the question is, one thing is they have told that it's a resistive load, right? So from the question itself, since they have mentioned that it's a resistive load, you understand that there is not going to be any necessity. There is not going to be any necessity for freewheeling as such, because question about freewheeling comes only if there is an inductive load. Over here, they have given that it's a resistive load. So directly you know that the freewheeling diode is not going to conduct at all. Correct? So the
Yes, sir.
freewheeling conduction, yeah, freewheeling diode is going to be um, off. Therefore, the option is either 0, I mean either A or D. So yeah, of
Mm.
course, you understand that since the thyristor starts conducting from the angle alpha, the conduction period is going to be pi minus alpha, right? So
Yes, sir.
each, yeah. So T1 is going to conduct for pi minus alpha period. Therefore, the option is option D, pi minus alpha.
5 minutes and 43.
Yeah. Okay. Okay. In a three-phase, three-pulse M3 type controlled converter, it's a three-phase control converter and it's a three-pulse converter, right? So I guess you're able to imagine the three-pulse converter. Anyway, I have the slide. T1 starts to conduct at 30 plus N degrees. At what angles do T2 and T3 start to conduct? Okay. So again, in this question, I think you are able to guess that since it's a three-phase repulse converter, the conduction of each of the thyristors is phase shifted by 120 degrees, right?
120 degrees.
Correct. So obviously, if T1 starts conduction at 30 plus N, the others T2 and T3 will start at 150 plus N and
And
270
then
plus N
70%.
respectively. Correct. So
Yes, sir.
I guess it's option B. Yeah, and that's what is shown over here as well. So only then you will be getting this profile of output voltage. Correct.
Yes, sir.
Okay. So then I will move on to the next question. Okay. So this is a kind of question with DC-DC converters. In case of a constant frequency system, T on is 1/4 of the time period. If T is your entire time period, T on is 1/4. If the chopping frequency is 2 kilohertz, find the value of T off. So they have given Fs as 2 kilohertz, from which you can understand that your T, capital T, is going to be 1 by 2 kilohertz, right?
Yes, sir.
Correct. So since you have your information about T and your T on is also available, you can also find T off, right? T off is going to be T minus T on. Correct?
Yes, sir. Yes, sir.
Yeah. So you just plug in the values over here. T is 1 by Fs and T on is 1/4 of that. So you can find out that it's 3 by 8 milliseconds. Okay, so the option is B, 3 by 8 millisecond.
Right.
So do I need to stop a little and go, or is it fine? Like, are you able to follow, or you also need to solve the questions while we go ahead? It's
No,
a
like up to here, like I'm following, sir.
okay, okay, fine. Okay, thank you. Okay. In the current limit control method, the chopper is switched off when dash. Load current reaches the lower limit, load current reaches upper limit, load current falls to zero, none of the above. Okay, so again, this is a current limit control, which means that your current is going to be controlled anywhere between Imin and Imax. Correct?
Yes, sir.
So the chopper is switched off when what? So the chopper, when the chopper is on, you understand that the load is going to get charged or the L is going to charge up. Correct?
Yes, sir.
So when the load current reaches the upper limit, you don't want the load current to increase further, right? So during
Yes.
that, at that instant, you turn off your chopper so that the inductor kind of freewheels, right? So the answer to this question is obviously B, right? So when the load current reaches the upper limit, the chopper is turned off and the load kind of freewheels, correct?
Yes, sir.
Yeah. Good. Um, yeah, so that's what I've given over here as well. And then we move out to the next. A step up chopper has input voltage of 220 volts and an output voltage of
Uh,
66. Yeah, yeah, yeah.
like, what is the application of this type of chopper, sir? Like, where we don't have any capacitor but only RL load, sir.
Sorry, I didn't understand.
So, what is the application of this kind of chopper circuit, sir? Where we only have RL load but no capacitor and EMF.
Um, See, for example, you take a DC-DC shunt motor, right? Let's
Yes,
say
sir.
that you are feeding the motor directly from the chopper, correct?
Yes, sir.
So you understand that the armature windings of the motor, um, for practical purposes, let's say we neglect the armature resistance. Of course, armature resistance is there, but you understand that because of the armature windings, your L is going to dominate a lot,
Yes,
right?
sir.
And
Yes,
it
sir.
is kind of directly across your chopper, right? So
Yeah.
you can actually, I had one picture, I guess, over here, right in the start. Yeah, so over here, the entire load side can be the entire load side that you see over here, that's your R and L, can be um, approximated as your armature winding.
Yes, sir.
Okay, so in that case, you tell that it's almost an pure inductive, almost a pure inductive load, right? Because your RA is very small.
Yes, sir.
Okay. Therefore, you will not see the RL type of a transient like you will not see some e power minus R by L kind of a graph. You will see almost a straight line. That's what I have drawn over here as well, right? I mean, Timax.
Yes,
So
sir.
this is a potential application. So far, as an answer to your question, right? So what you can do is you might have studied techniques about armature voltage control in your machines course, wherein you try to control the armature voltage, right, for controlling the speed eventually and the torque.
Yes,
So
sir.
of course your chopper can be used for that. So if you control your on time of the on time of the switch, if you vary the duty, then you're obviously controlling the output voltage. And you know that your inductor is quite large, therefore your current is going to be almost constant, right? You
Yes, sir.
can very well use it for DC-DC, DC motor applications. Okay. A step-up chopper has an input voltage of 220 volts and output voltage of 660 volts. If the conducting time of thyristor chopper is 100 micros, then what will be the pulse width of the output voltage? Okay. So the question is step-up chopper. So step-up chopper means obviously you understand that it's a boost converter, right?
Yes, sir.
So it has an input voltage of 220 volts, that's Vs is 220, and the output is V naught, which is 660 volts. So you have a jump or a gain of 3, right? 220 to 660, correct? Therefore,
Sir.
you may of course know that the duty of the boost converter or the gain of the boost converter is given by 1 minus d, right? V naught by Vs is going to be given by 1 by 1 minus d,
Yes, sir.
correct?
Yes, sir.
So, so your 3, the value 3 is equal to 1 over 1 minus d, or your 1 minus d equal to 1 by 3, or d is what? D is 2 by 3, right? Correct?
Sir.
So the conducting time, so then the question is if the conducting time of the thyristor chopper is 100 micro, then what will be the pulse width of the output voltage? So you can just use this relation. So you see that D is 2 by 3, therefore your turn off period, right? So
Yes, sir.
that is the duration for which you are going to get the output voltage, right? T off. Do you understand why we have calculated T off over here?
Yes, sir.
The do you understand why we have calculated T off? The question is, see, what will be the pulse width of the output voltage?
Yes, sir. Yes, sir. To
Okay.
calculate T, sir.
Yeah, so the point is they have not asked the pulse width of the switch. They have asked the pulse width of the output voltage. So you need
Yes, sir.
to see this very carefully. So in a step-up chopper or a boost converter, you know that from 0 to DTS period, right?
Yes, sir.
0 to DTS period, your switch is on or your L is charging, right?
Yes,
L
sir.
charges. Okay. Therefore, during this period, V naught is maintained only by the output capacitor. Correct?
Yes, sir.
So this is not actually the pulse width of the output voltage. Your switches are not your switch is not coming across your output voltage, right? During this
Yes, sir.
period. But when the inductor is discharging, right? During that period, you know that your inductor discharges to the output, correct? To the output side. So that is actually the period that's mentioned in the question. What will be the pulse width of the output voltage? So when does the output side get connected to the input side? That's the question they have asked. Okay.
Yes, sir.
For what duration the output voltage gets connected to the input voltage, right? So that duration is obviously T off, right? Because during T on the inductor charges only through the switch. Correct. During that period,
Yes,
V
sir.
out is not connected to V in. But during the T off period, V out is connected to V in through the inductor, right? The diode gets forward biased and therefore you have V in, inductor and V out. Correct? So that is why in this quiz, for this question, the answer is you need to calculate your T off.
Yeah. Also.
Okay. So you got it?
Yes, sir. Also.
Okay. Okay. Thank you. Good. Um, okay. A three-phase bridge rectifier charges a 240 volts battery. Input voltage to rectifier is three-phase 230 volts 50 hertz. Okay. So current limiting distance in series with the battery is 8 ohms. So R is 8 ohms, right? So R is 8 ohms. And then you have a three-phase bridge rectifier. 240 volts battery means E is 240 volts. And the inductor makes the load current almost ripple free. Calculate the current distortion factor. Okay. So this question, I think we did it in the last class. That is the current distortion factor, as you may know, is given by the fundamental value of the input current to the total RMS value of the input current, right?
Yes, sir.
Correct.
Yes,
So
sir. Yes.
we call it by different names. Some people call it CDF, some people call it by the name G or the variable G and stuff. But anyway, it is something that's fixed for three-phase bridge rectifier, irrespective of whatever may be the value of your battery or whatever may be the value of your load resistance.
Yes, sir.
Okay. So I think we did it, and if I remember correct, we got the answer to be somewhere around 0.95. Correct? For single phase, it was zero point 0.9, and for the three-phase case, I think it was 0.95. However, for the sake of easiness, if you want, I can redo it. So, do you want me to redo it?
So I will check last week's lecture, sir.
Okay, I think we have done this. We solved a similar question in that we got the answer as 0.955. Okay.
Yes,
So I
sir.
think I was mentioning about the input current being something like a square wave. Sorry, I drew it wrong. Input current was something like a square wave. So you have something like this, correct? And
Yes,
of
sir.
course, your RMS of fundamental your fundamental is going to be something like this. So you just have the RMS value of this sine wave and the RMS of the square wave, and then you just go ahead and divide it, right? So
Sir.
it turns out to be around 0.955 if I'm not wrong. You can just go and check it once. Or else if you want it, no worries, I can solve it if you want.
No, sir, it's okay, sir. I will check it, sir.
Okay, so in the end, if we do have time, then maybe I can solve, okay?
Yes, sir. Yes, sir.
Okay, okay, thank you. Answer is 0.955. Okay, so for the sake of easiness, I will just write the Fourier series expression over here. So your input current Is is given by sigma n equal to, of course, odd to infinity 4 I naught by n pi. And since we are dealing with three phase, you of course have a sine term, sine n pi by 3, and then sine n omega t. Okay. So from this you can calculate what is IS1, right? So IS1 RMS is given by 4 I naught by pi sine pi by 3 over root 2. Correct? So that will be your IS1 RMS. So 4 I naught by pi sine pi by 3 over root 2. So this is your IS1 RMS. Correct? Oh, probably I should have written it here. Okay. So you have your IS is 4 I naught by n pi sine n pi by 3 sine n omega t plus pi n. Correct? So your IS1 RMS will be given by 4 I naught by pi. Sine pi by 3 is sine 60, which is root 3 over 2 over root 2. So this is your IS1 RMS. Okay. And of course, you know that IS RMS is given by um, your I naught into root over 2 by 3. Okay, so you just go ahead and divide. So current distortion factor or the CDF, your CDF is going to be IS1 RMS over IS RMS. So that will turn out to be 0.955. 0.9549 or something is what we got, I guess. Okay. So your IS was something like this. Okay. So for this kind of a waveform, the RMS is, of course, this is still 120 degrees, 180, and this is 360. So you understand that in this out of 360, the IS is on for 240 degrees. Therefore, the RMS is I naught into root over 240 by 360. That's how we end up with I naught into root over 2 by 3. That's the RMS of the source current, and the fundamental, of course, you calculate from the Fourier series. So you just go ahead and divide the fundamental with the total RMS and you get 0.955. So yeah. So irrespective of what they have question given in the question, it's a 240 volt battery, 8 ohm or 10 ohm rectifier, inductor, whatever may be the question, you know that the current distortion factor is kind of fixed for a three-phase bridge rectifier case, right?
Yes, sir.
Similarly, for single phase, it will be 0.9 if I'm right.
0.9. Yes, sir. 0.9.
Okay. Okay. The three-phase bridge rectifier charges a 240 volt battery. Input voltage same. Input voltage is three-phase 230 volt 50 hertz. Current limiting resistance in series with the battery is 8 ohms, and an inductor makes the load current almost triple free. Calculate the power delivered to the battery. So in this case, you of course need to draw the equivalent circuit, right? So you have something like this. you have your V naught, which is coming as the output of your three-phase bridge rectifier. You have your R and E, and you just apply KVL, right? So you just apply KVL over here. Uh, you know that what is V naught for a three-phase bridge rectifier? 3 Vm L by pi cos alpha, correct? Correct. So here it's a diode bridge rectifier, I guess. Therefore, cos alpha is also 1. And VML means the maximum of the line to line voltage. So 3 into 230 into root 3 into root 2 by pi. That's your V naught. Then you of course know that by KVL, V naught is E plus I naught into R. Correct. So you can compute what is your I naught for from over here. Therefore, the power delivered to the battery, that's the question. So power to the battery is E into I naught. Okay, so read the question properly. The power can be calculate the power delivered by the converter can be one question. The other question can be calculate the power delivered to the battery. So specifically to the battery means you need to multiply with E. Okay.
Yes, sir.
So that's what I have shown over here as well. It's just the output voltage of your converter 3 ml by pi, and we know that by KVL this is coming. So you can just find out what is I naught, and power delivered is E into I naught. Okay. Okay. A single phase full converter has discontinuous load current. The converter is supplying a DC shunt motor. Shunt motor is an RLE load, obviously. So when the current falls to zero, the output voltage is what? Okay. So you have a single phase full converter, which I'm again not drawing. So you have R, L, and E, right? So V naught is there, I naught is there, R, L, and then E. Okay, so when the current falls to zero, what is the output voltage? So if the current is zero here, can you tell me what is the output voltage?
E, sir, it will be E.
Obviously, right? Because current is zero, therefore there is no drop across the resistor, and obviously there is nothing across the inductor as well. Therefore, the output voltage will be E. Good. Okay. In a semiconverter with RLE load, during the freewheeling period, this is very simple. So during the freewheeling period, energy is what? Energy is fed back to the source, fed to the inductor and absorbed by E, absorbed by L and D and dissipated at R, fed to L and D and dissipated at R. Okay, so for these type of questions, first draw. Okay, it will be easier for you. Hmm. So the point is in a semiconverter, you have something like this, and then you have your R, L, and then your E. So the question is during the freewheeling period, what happens? You of course know the inductor current is going to be something like this, correct? So in this itself, you can answer from the load side, from the load perspective, right? So you see that the current is going something like this. Okay. So I naught into R. So there is going to be an I square R dissipation over here. Correct. So there is going to be a dissipation at R. Okay. Second thing is, of course, I naught is going to flow through the inductor, right? Therefore, it's going to be, mm, um, it is going to be through the inductor and then through the battery EMF, correct? So can you tell me which of the options it is, whether it is C or D?
D, sir.
Okay. So why do you think so?
Sir, because inductor doesn't absorb energy.
Correct. Correct. Okay. Fine. You're right. You're right. Inductor cannot absorb energy. Inductor can only store energy, right? So it cannot absorb energy. So if you feed it, it only just stores energy. Okay. Okay. A single phase 230 volt 1 kilowatt heater is connected across a single phase 230 volt 50 hertz supply through an ACR. For a firing angle delay of 45 degrees, calculate the power absorbed in the heater element. Okay, so it's a single phase converter. I think there is a typo over here. A single phase converter, full converter. Okay, so for firing angle of alpha of 45 degrees, calculate the power absorbed in the heater element. So one thing is you understand anything, any talk about heating element, it means that there is a resistor inside it. Okay, therefore the power can be given as I square R if you calculate I, or even simpler, you just calculate what is your V naught. Therefore, the power is V naught square over R. Okay, so they have given you the power. Therefore, P is given to you, correct? You can always find out what is your R value over here. Okay, so yeah, so how do you solve this? One thing is, as I told, the power dissipation, right? You talk about resistor. One thing is, if you talk about heater, you're talking about some resistor inside it. Okay. And if you talk about resistor, you're always talking about heat dissipation through the resistor. Okay. When you talk about heat and dissipation, you always talk about the RMS values and never the average values. Okay. So you tell that what is the power delivered to the load? P is equal to V naught I naught. That's your average value. V naught average, I naught average. Over here, you should observe very carefully that the question is calculate the power absorbed in the heat element, or better word would be power dissipated in the heat element. In that case, you always need to take the RMS. So P over here refers to V naught RMS square over R. Okay, never take the average value. Okay. So you of course know to calculate the average value as well, right? Like if you calculate the average value and do it, you are going to end up with the wrong answer. Okay. Always take RMS value into account. Okay, because it's you are having a heater has a resistive element inside it. So heater has an R. So R means you always talk about dissipation, right? And means there is going to be a heat. If you know the general or the generic definition of RMS or root mean square, it comes from the equivalent amount of current that generates that much heat, right? So that's all. That's basically your RMS. Therefore, you always need to take RMS quantity. Okay, never take the average quantity. Never calculate it as V naught average square by R. It's always V naught RMS square over R. Okay. Use the formula for V naught RMS for a single phase converter, and then you'll just end up with the answer. It's a pretty simple question. Okay, so we have seen this question also. So V naught RMS is Vm by 2 root pi into root over pi minus alpha plus sine 2 alpha over 2. I guess we derived this formula in the last class as well, right? Um, Sudarshan, are you there?
Yes, sir. Yes, sir. We did it, sir.
Yeah, so is this fine? Like we derived V naught RMS, and in that you just substitute the values for alpha and you end up with V naught RMS. Therefore, the power is V naught RMS square over R. Okay. In the options, one of the options will always be V naught average square over R also. Okay, just for the sake of trapping you guys. Okay, so please remember, it's always a heater resistance. And always heater resistance means you always have an RMS quantity. Okay. Okay. A three-phase full converter fed from a three-phase 400 volt 50 hertz source is connected to a load R equal to 10 ohms, E is 350 volts and large inductance so that output current is ripple free. Calculate the input power factor when firing angle is 60 degrees. So there is a three-phase full converter. Obviously if it's from a three-phase source, you have a three-phase full converter. R is given, E is given. Okay. Large inductance so that the output current is ripple free. Calculate the input power factor when firing angle is 60 degrees. Okay. So always the reason all these quantities are given is okay, the moment a student sees this question, he will not think about this particular term, input power factor. The guy will be thinking about, okay, R is given, E is given, and also the input VM is given or the VS is given. So I can always calculate what is VS for this full converter. Okay, I mean, what is V naught for this full converter? Okay, so immediately the student will solve it, find out what is E naught because alpha is also given as 60 degrees. He will find out what is V naught, 3 VML by pi cos alpha. After that, he will start thinking about what is the input power factor. But the question has nothing to do with your V naught average. Okay, question is simply input power factor. Okay, so you always note one thing. We earlier we saw what was the current distortion factor, right? The current distortion factor turned out to be 0.955. Correct? We saw this in one of the previous questions as well. For a three-phase full converter, the current distortion factor is 0.955. If you go through the basic definitions that you saw in, I think, in as part of week 2, over there you saw what was the input power factor, how it was related to the current distortion factor and stuff, and your firing angle and stuff. In that, one of them was that your input power factor, right? Input power factor is actually current distortion factor times cos alpha or the firing angle, cos of firing angle. Okay. So this is the input power factor. So the input power factor is 0.955 into cos 60. Okay, so cos 60 is 1 by 2, 0.95 over 2 is 0.4775. Okay, and of course it is lagging. Okay, and because they have told that it's a very large inductance, therefore it's always going to lag. The output current is going to lag the output voltage. Correct? Simple. Therefore, the option is either B or C. That is fine. One thing is they have asked the input power factor, which is current distortion factor times cos alpha. Okay. So cos alpha is cos 60, which is 1 by 2, 0.9555 into 1 by 2 is 0.477, right? So the answer is 0.477 lagging. Okay. So if you guys see the question, please don't do it like, okay, so we have got all the resources for calculating V naught. Let me calculate V naught. After you calculate V naught, you realize that V naught has nothing to do with your input power factor. Okay. So never do that kind of a mistake. So far, have you been able to follow,
Yes,
Sudarshan?
sir. Yes, sir. Yes, sir.
Okay, good. So far you have any doubts or you want me to repeat anything?
Sir.
Sorry?
No, sir. No, sir. Like I'm following, sir.
Okay, good, good. Thanks. Okay, so we will just have a 3-4 minutes break and then after that we can start. Okay, we can continue. Okay,
Yes, sir.
you can also have a break for around 3 or 4 minutes. Then after that, we'll just see some more example problems. I thought today we covered a lot of problems from rectifiers because I thought it's good to cover extra problems. But now we will go ahead with DC-DC converters. We will try to solve some problems. If you have a calculator, you keep it as well because I have not added ready-made answers for those problems. On the go, I'll just dictate or I'll just write down the parameters and then we can solve it. Okay. A few problems we can just solve and then close for the day. Okay. Okay. So you have a break. Okay. You can come back at around 6:55 or something. We can just start ahead from that point. Okay. So can the others tell if they have been able to follow? If any one of you can unmute. Do you want me to repeat anything? Or is this fine? Or you can just type in the chat box if you have any comments. Okay, so we'll just have a 3-4 minute break and then we can start. Okay, so we'll just go ahead. We will see a few more problems and then yeah, I think we should be able to close for the day. We have seen around 15. We'll just see a few more and then we can close. So I would request all of you to please have your calculators in hand. I also will do side by side. So it will be easier if you get a hands-on, I mean, if you have a hands-on experience of solving problems. Okay. Okay. We'll solve this. So this is problem number 16. Okay, the question is in a buck converter, the voltage across the inductor varies from voltage across the inductor VL varies from 30 volts to minus 20 volts. 30 volts to minus 20 volts. Okay. Calculate the duty. Okay, calculate the duty or the period for which the switch is on. So that's the question. Okay, so the question is the voltage across the inductor varies from 30 volts to minus 20 volts. Calculate the duty. So for such questions, it would be better if you actually draw the converter. Okay. So in a buck converter, you have something like you have the switch over here, and then you have the inductor on the output side, and then you have the diode over here, and of course you have the load. So this is your buck converter, and um you call this as your V. You call this as your V in. This is your V naught, and the conventional idea is something like this. Okay. So when would it be 30 volts? Obviously, when this inductor is, when the switch is turned on, VL is V in minus V naught, correct? And when the switch is turned off, VL is going to be minus V naught. So from this, you correlate with the given data, you end up with V naught being 20 volts and V in being how much? So V in being 50 volts. So V naught is 20 volts. V in is 50 volts. Correct? So now that you have V naught and V in, you can find out what is your duty. So your duty for a buck converter is V naught over V in. Correct? So that is 20 over 50 or 2 by 5. 0.4 or 40%. Okay, so got this question? They have given the voltage across the inductor. They have mentioned that the voltage across the inductor varies from 30 volts to minus 20 volts. Calculate the duty or the period for which the switch is turned on. Okay. So you know that in a buck converter, VL is V in minus V naught during the switch on period and VL is minus V naught when the switch is off. So you just correlate both these information and you end up with what are the values for V naught and V in. Therefore, V naught over V in is your converter duty, and in this case, for buck converter, the converter duty is also D. Therefore, the D is 0.4 or 40%, right? So, yeah, I think this was a pretty simple problem. We'll just move on to the next one. If you don't have any doubts, if you have any doubts, of course, you can stop me. Okay. Um. So the question is, the switch duty is 0.4. Okay. The switch duty is 0.4 and Vs supply or the V supply voltage has been mentioned as 20 volts. Okay, so you have a buck converter. Again, this is a buck converter. So in the buck converters, the supply voltage is 20 volts and the duty is 40%, or the switch is on for 40% of the total time period. Okay. The buck converter is feeding a load of, it feeds a battery having an EMF of 5 volts and a current limiting resistor R of 3 ohms. Okay. So the buck converter is feeding a load of 5 volts battery in series with a 3 ohm resistance. Okay. So this is the load. Find what is the load current I naught. Okay. So find what is the load current. So that's the question. Okay. So the point is you have something like this. You have something like this. Correct? So you have your E, and then you have your R. Find out what's your I naught. That's the question. So this is again a pretty simple problem. If you find out what is V naught is going to be E plus I naught times R. This is one. Second, for a buck converter, V naught is D times V in, or the V supply. So both of them are given over here. You can just find out what is I naught, right? You just cross substitute and you get it. Correct? So if you do this V naught, you will be getting us D times Vs, right? So 0.4 times 20. Correct? So 20 into zero point 0.4 is going to be your 8 volt. Correct? So 8 is equal to E plus I naught into R. That is 5 plus I naught into R. R is 3. Therefore, I naught is 1 ampere. Correct? You got it right. So again, I guess this is a pretty simple problem. If you have any doubts, you can, or you want me to repeat, you can of course ask me. Okay. So then if you don't have any doubts, we can move over. Hmm. It's going to full screen. Hmm. Okay, I don't know why it's not going to full screen, but anyway. Uh, okay, so the next question is, okay, I don't know why it's not coming anyway. Um, I'll just save this once and then we will open a new one. So I don't know why it's not going to full screen mode. Anyway, I will then use a new one. Save. So are you able to see my screen?
No, sir, it's not visible on the screen.
Um, okay, and then just give me just a second. Slideshow, current slide. Okay, now is it visible?
No, sir.
Just now is it visible?
Yes, sir, it's visible.
Okay, thank you. Slideshow. Okay. Okay. Sorry for the anger. We'll just go ahead now. So this question is, it's an interesting question, this particular one. So the question is, um, you have a buck converter which is operating at a switching frequency of 100 kilohertz. Okay. So I have a buck converter which is operating at a frequency of 100 kilohertz, and the switch of the buck converter is operating at a duty of 60% or 0.6. Okay, duty of 0.6. The output voltage has been built up to 36 volts. Output voltage has been built up to 36 volt with the supply voltage or Vs being 60 volts. Okay, so Vs of 60 volts and the output voltage is 36 volts. Okay. The buck converter features an inductor. The inductor of the buck converter is specified to be 5 millihenries. The buck converter features an inductor of 5 millihenries, and the current or the I naught is just continuous. So it is given, or sorry, the IL or the inductor current is just continuous. Okay. Find out the load resistance. Find the load resistance. You got the question? So we have a buck converter which is operating at a switching frequency of 100 kilohertz, duty of 0.6 or 60%, V naught is 36 volt, Vs is 60 volt, right? L is 5 millihenries. Okay. It is given that the inductor current is just continuous. Okay. Find the load resistance. Okay. So from the question, what do you understand? You understand that the inductor is going to be just, the inductor current is going to be just continuous. Okay, so it is neither in the CCM mode nor in the DCM mode. It has just come out of DCM mode. Okay, got it. So how do we solve this? So it has something to do with inductor value, right? So you understand that the ripple depends on the amount of inductance. So higher the value of your inductor, lesser will be the ripple. And the higher is the probability that the conductor is operating in CCM mode or continuous conduction mode. Correct? So this L, or as I call it LC, this is the critical value of the inductance or the minimum inductance which is required to maintain the inductor current just continuous. Under this condition, find out the load resistance. That's the question. Okay. Okay. So conventionally, what do you know about the inductor current? So the inductor current is for a buck converter or any converter is going to be something like this, correct? So it is something like this. You call this total peak to peak ripple, right? You call this peak to peak ripple, and this is your average inductor current, or I will call it as I naught. You have got I max over here and I min over here. Okay, you have got I naught, and you have also got the ripple value, right? Your ripple is delta IL. Delta IL is your peak to peak ripple, or I max minus I min. Okay. Now they have mentioned that the inductor current is just continuous, which means that your inductor current is something like this. It is just continuous. Okay. It is touching zero, not going below zero. Okay. And it is just continuous. It's not above zero as well. It's not somewhere here. This is, we are in this case right now. Okay. It is just continuous. This is your I average, and you have your I max, and your I min is obviously zero. Okay. So in this case, I min is zero. And what will be Imax? Imax will be equal to delta IL, correct? Because this happens to be delta IL. Okay, this is your Imax. This point is your Imax, and your therefore your Imax will be equal to delta IL. That is the peak to peak ripple is actually equal to your the peak current of your inductor. Okay, Imax is delta IL. So what about your I average? I average or IL average as I call it. IL average will be delta IL over 2, right? So this is your IL average. Okay, so your IL average is delta IL over 2. Okay, so what is the IL average in a buck converter? In a buck converter, let me go over to the next slide. In the buck converter, you have something like, correct? And then you have your load. Okay. So you have something like this. You have your R, you have your L, C, D, and then you have your V in and then V naught. So what is your IL average in a buck converter? So your IL average is equal to I naught average. Okay. So your IL average is equal to I naught. Okay. I naught is obviously V naught by R. Okay. So just, you know that IL average is delta IL over 2, right? That is the peak to peak ripple over 2. That is your IL average. And you know your I naught average is V naught over R. So from this, you know what is V naught, and if you know what is delta IL, you can find out what is R. Correct? That is your IL average is delta IL over 2. Delta IL over 2 is equal to V naught over R. From this, you can find out what is V naught. Okay. Okay. So what is this delta IL? So it is again a pretty simple relation. You know that VL is equal to L times di dt, di over dt. Okay. So VL is L times di over dt. Therefore, when the inductor discharges, right? So when the inductor discharges, VL is equal to minus V naught. Correct? When the inductor discharges, VL is equal to minus V naught. So minus V naught is equal to L into di is what? The di is inductor current is falling from the peak, that is I max, to 0. Correct? So di is delta IL, right? And what is dt? dt is the off period. Okay. So it is 1 minus dts. Okay. 1 minus d times ts. Okay. So if you rearrange this, you will get what is your L. L is V naught into 1 minus dTs over delta IL. Okay. Or or the other way around is delta IL um delta IL is given by V naught into 1 minus dTs over L. So you know what is your delta IL. Delta IL by 2 is equal to V naught by R. Therefore, you can find what is R. Got it? So do you want me to repeat this question? How the approach towards solving this question, or is this fine? Anyone? Can you please, or do you want me to repeat it once again?
Sir, once again repeat, sir.
Yeah. Okay. So you got the question right. So the question is that you have a buck converter. They have given all the parameters in the buck converter. Okay, they have given the switching frequency and then the duty of the switch. They have given the input voltage, output voltage. Two important things they mentioned is they have mentioned the value of your inductor. Okay, the buck inductor, main inductor, they have mentioned the value. That is one. Second thing is they have mentioned that the inductor current is just continuous. Okay, just continuous means, so you understand that the inductor current can be discontinuous as well, right? It's not that the inductor current will always be in the um, will always be here. It's not that the inductor current will always be here, right? The inductor current can be lesser. At some point, you will see that inductor current will be so low that the I minimum will become equal to 0. Okay. You will have an I max and then again it drops to 0. Okay. So you will probably be studying more about it. It's called the discontinuous conduction mode. But over here, what is happening is they have told that the inductor current is just continuous. That is, it starts from 0, it starts from 0, reaches an I max, and then it goes back to 0. Then again it starts from 0. Okay. So this is the question. Got it? Did you get the question? Can you please unmute and tell me? Hello? Are you there? Okay, no worries. So this is a question. The question is find out the load resistance in this case. Okay. So the idea is that okay. So since you are told that it's just continuous, your I min is 0. Okay, I min lower value of your inductor current is 0 and it reaches an I max and then it drops to 0. So you understand that delta IL, that is the peak to peak ripple or delta IL as we call it, right? Delta IL is between I min to I max. That is I max minus 0 over here, right? So delta IL is equal to I max 1. Second thing, what is the average value of inductor current? As you may know, is I max plus I min over 2, right? That's the average value of your inductor current. I max, it's the average, right? I max plus I min over 2. Over here, your I min is 0. Therefore, your I average or your IL average is I max over 2, right? We just saw that I max is equal to delta IL over here. Therefore, I am writing that your average value of inductor current is delta IL over 2. You see over here, IL is delta IL over 2. Okay. IL is delta IL over 2. So till this point, is it fine? If you can reply, it will be great because I don't know till how much you are following. Okay. Okay. So now that we have this, now that we have this information that IL average is delta IL over 2, what we can do is, okay, so we know that in a buck converter, IL average is I naught average, right? The average value of your inductor current is same as the average value of your load current. And load current is V naught over R. Therefore, is IL average in this case is V naught over R. Okay. IL average is V naught over R. So you know what is your V naught. You need to find out what is R, and you also need to find out what is IL average. Then you can find out what is R. Okay. So how do you find IL average? IL average, as we told, is delta IL over 2. Now I need to find out what is delta IL. Okay. So just take an inductor, normal inductor. In an inductor, the VI relation is given by V is equal to L times GI over dt. Right. You know that the voltage across this inductor, right? The voltage across this inductor is either V in minus V naught. So VL is V in minus V naught during the dTs period, or it is minus V naught during the 1 minus dTs period. Correct? So you can use either of these. Okay, you can either substitute VL as V in minus V naught, or I have taken minus V naught. So you can use VL is equal to minus V naught. So V minus V naught is equal to L into DI. What is DI? Change in current. Change in current is delta IL, right? That's the change in current, current ripple. So delta IL over the time. So what is the dt? Since we have considered minus V naught, it is 1 minus dTs. You rearrange this, you will get delta IL is equal to V naught into 1 minus dTs over L. Okay, so this is your delta IL. We saw that IL average is delta IL over 2. So this over 2 is equal to V naught by R. Therefore, find out what is R. Got it? Uh, please, can someone tell me if you guys got this question till this point, like how we have solved?
Yes, sir. Understood, sir.
Understood?
Yes, sir.
Okay. So now you need to find out what is R. So can you guys do it? Can you guys help me do it, or? Okay. So the point is, delta L is V naught into 1 minus dTs over L. So delta L is V naught into 1 minus dTs over L, or I will write it as L into Fs, right? So you find out what is this. V naught is given as 36 volts into 1 minus D is 0.6 over L is 5 millihenry. So 0.005 into Fs is 100 kilohertz. 100 into 10 power 3. So you can find out what is delta IL. So can someone do it and tell it to me? What is delta IL? So once you find out what is delta IL, then you know that IL average is equal to delta IL over 2. Okay. Now IL average is the same as I naught average. Therefore, I naught average is equal to V naught over R. Therefore, R is V naught by I naught, right? So V naught is given as 36 volts. 36. You can compute what is I naught, and that will give your ohms. So can someone do it and tell it? Can someone tell what is delta IL? Please, in the solving sessions, it will be good if you have your pen and paper together instead of just staring at the screen.
0.0288.
Okay, so this is your 0.0288. Okay, so this is your delta IL, and then so your IL average will be 0.0144 amperes. Correct? So 36 divided by 0.0144. How much are you getting?
625.
625. Sorry,
625, sir.
625. Okay. Okay. So all of you, please do check this problem. All of you, you are encouraged to solve the problem by yourself. Okay. You check the numbers. You check how we have arrived at this answer. It will be easy for you. Okay. Okay. So till this point, I've got any doubts, or can we just go ahead and solve a few simple problems and then we can close off for the day?
Yes, sir.
Okay. Hmm. Okay. I have a similar question to what we saw over here, question 16. I have a similar question for boost as well. So the voltage across the inductor in a boost converter switches between 15 volts and minus 45 volts. Okay, the voltage across the inductor in a boost converter switches between 15 volts and minus 45 volts. Find out the duty of the switch. Find out the duty period. Okay, again, it's a very simple question. Just have your boost converter at hand. So you have your L, then you have your switch, and then you have your diode. Correct? So this is your VL, V in, and then V naught. So you understand that when the switch is on, VL is going to be V in, right? When the switch is on, VL is going to be V in. So this is during the DTS period. Okay. And when the switch is off, the voltage across the inductor is going to be V in minus V naught. Okay. This is during the D dash TS or 1 minus DTS, as you may call it. Okay. So you understand that in a boost converter, V naught is always greater than V in. That is why V in minus V naught is negative and you have a minus 45 volts over here. Okay. So you just plug it. V in is 15 volts, right? Um, V naught, how much will you get? V naught is 60 volts, correct? If you do this. Therefore, what is D in a boost converter? V naught by V in is 1 by 1 minus D. You know what is V naught? You know what is V in? You can find out what is D. So D will be 60 by 15 is 4. So 1 by 4. So D will be 3 by 4, right? Or 0.75, 75%. Okay, this is again a very simple problem, right? The voltage across the inductor is given, just correlate with what you expect as the output voltage and you will get the answer. Okay. Okay. So any doubts in this question or we can go ahead with the last problem for the day? Okay. Okay. So the question that's given is in a buck boost converter. So are you guys aware of buck boost converters? So was it covered? Can anyone please reply?
Yes, sir, but not that much in depth, sir.
Yeah, it's a very simple question, similar to the previous question only. I will anyway draw the circuit, it will be easier for you. So you have your buck boost converter. It's a buck boost converter problem. So the question is the input, okay, so the output voltage is maintained constant at 48 volts. So it's a battery charging problem. So you have a buck boost converter which is charging a battery and the battery output voltage is maintained at 48 volts. Okay. The input voltage is also obtained from a battery. The input voltage varies anywhere between 32 volts to 72 volts. Correct? So the input voltage varies anywhere between 32 volts to 72 volts. So you see over here that there is a buck and boost both, right? 32 to 48 boost is happening and 72 to 48 buck is also happening. Okay. So the input voltage ranges from 32 to 72. V naught or the output voltage is 48 volts. Okay. Correspondingly, find the range of variation in duty. So they have mentioned Vs minimum is 32 volts and Vs maximum is 72 volts. Like that, what is D minimum and D maximum? Got the question? Okay. So for this particular problem, I will just draw the buck boost converter. Then I guess it will be easier for you. So you have something like a switch over here and an inductor, right? Okay. So once you have the circuit, just you need to analyze when the switch is on, what happens, when the switch is off, what happens. Okay. So this is your VL, this is your V in, and this is your V naught. Okay. So what is VL? When switch is on, VL is V in. Correct? When the switch is on, VL is V in. And when the switch is off, VL will be, this diode gets forward biased. Therefore, VL will be what? VL will be V naught. Correct? So this is during the DTS period and this is during D dash TS period. Okay. So in a buck boost converter, the conventional direction of your output voltage is actually reversed, which means that it's going to be minus V naught. Right? Okay. So anyway, the output voltage or the gain of the buck boost converter is given by V naught by V in is equal to D over 1 minus D. Okay. Now, one case is V naught is 48 volts, Vs is 32 volts. So 48 by 32 is equal to D by 1 minus D. This is one case. And the second case is 32 to 72 volts, right? So V naught by V in. So 48 by 72 is equal to D by 1 minus D. So find out what is the value of D in this case and find out what is the D in this case. So this will be the minimum value D minimum and this will be D maximum, I guess. Okay, so this is the range of duty. The question is find out the range of variation of duty. So just substitute the values for your converter gain and you will get what is Dmax and Dmin. Okay, got it. So in this question, you have any doubts? Okay. So if you don't have any doubts, then actually I think this was the last problem I had. I had totally a total of 20 problems. So I think we were able to cover all of them, right? So at this point, if you have any doubts, this is the right time to ask, or else we can actually close today's session. Okay. Initial 10 problems were mostly focused on rectifiers, and then after that, we solved quite a few problems on choppers as well. Okay. So I think the problem that you found difficult a little bit was all others were fine. The only thing was this problem, right? The just continuous question, correct? I think that is what you would have found a little difficult. But no worries. I think as the next week goes by, I think this should be clearer to you. We will be covering about these in detail. So I think it will be easier for you to answer that particular problem. Yeah, this particular problem. But anyway, next week we can perhaps see um, a few more problems in this topic, so it will be easier to you, or you will get familiarized with this. Okay. So this was just to introduce you to these kind of problems as well. But anyway, the next week we can see in detail perhaps. So you need not worry too much if you didn't get this particular problem. But yeah, I think all other problems were pretty easy on non-isolated converters. So if you have any doubts, you can go ahead and ask, or else we can close the session. I'll just pause for maybe two, 2 seconds. Okay, so just check the chat. Okay, so if you don't have any other doubt, then we can close today's session. Have a great week ahead, everyone. And yeah,
Yes, sir.
yeah, thank you, Sudarshan, for attending. Thanks, Bhagya. Thanks, Pawan. I'm closing the session now.